Okay, good morning. This is Professor David J. Delos Okay, my topic for this session will be still easy machines, and we are now on lesson number 68, and this is with regards to the so-called parallel operation of alternators. Okay, let's proceed. The date for today is December 23, 2023. Okay, Merry Christmas to everybody. Okay, let's proceed. The subject matter for this morning will be a long video format discussion, and this is with regards to my long video format topic, AC machines. And this is now lesson number 68. And the title of the topic for this morning will be an example problem on the so-called parallel operation of alternators. So we have here an alternators that are connected in parallel. It's just only two for simplicity, right? And we operate it in parallel. Okay, I will try to, what you call this, give you the specs of the problem. We are given a 1000 kVA, 3-phase, 60 Hertz, 13,800 or 13.8 kV alternators. These should be alternators. This is 2. Okay? They are Y connected, and they have the so-called identical load and speed characteristics. Meaning to say, speed and load characteristics, meaning to say these two alternators are almost similar. The physical characteristics are the same. That is with respect to load and speed, and operates in parallel, sharing a load equally. So meaning to say, if they have the same identical load and speed characteristics, just in case we will try to, what you call this, operate them in parallel, they will share the load equally. Okay? So it's a balanced thing. The other one is not overloaded, the other one is not underloaded. So they will try to, whatever load that will be connected on the bus bar, okay, they will try to supply that load equally with the same current. Okay? Same true power. And the load that is connected on the bus bar is 1,600 kilowatts. Power factor is 80% lagging. Power factor lagging meaning the current of this load, okay, lags behind the phase voltage by a certain angle, the theta. That's why it says here the power factor is 0.8. I forgot to place this one. It should be lagging. Okay. The requirement of the problem is, there's a given condition. The field excitation of the two alternators. Of course, there's an exciter for both alternator A and B. Is adjusted such that the current delivered by alternator letter A is 40 amperes. The current is just 40 amperes. So it seems the load is small. It's not. Why? Because the voltage here is 13,800. It's a big voltage, small current, so it will still be a big power. Okay? That is on the so-called alternator side. Big voltage, small current, okay, it will still be a big power, right? The problem is asking what will be the value of P, meaning the true power carried by each alternator and the power factor of each. The problem is asking what will be the total power delivered by generator A and generator B, and also with regards to the so-called PF, meaning power factor. The problem is just asking what will be the load carried by alternator A and alternator B, and what will be the respective power factors. Okay? Okay, let's try to bring out the so-called single line diagram. We are now talking here as an electrical engineer. So if we try to draw the graph of this, we will be using the so-called single line diagram. So it seems we are now reading an electrical diagram professionally done, right? It is so-called single line diagram. Or it is something like this. This circle thing represents the alternator A and alternator B. This line here is just one line, but it's one line, but if you try to read the electrical diagrams under single line diagrams, if there is a three slash like that, it is considered to be three-phase. Right? So this is a three-phase line, this is a three-phase line. Okay? They are connected to a load. Again, this is a three-phase line. So of course, this load here is three-phase. So this is three-phase line, this is three-phase line. And the load is 1600 kilowatts. The power factor is 0.8 lagging. Okay? The given condition of the problem is the current delivered by alternator A is 40 amperes. So the problem is asking what will be the total true power delivered by A and what will be the power factor of A. And the other thing is what will be capital letter P with the subscript B, meaning the total true power delivered by alternator B, and what will be PF with the subscript B, meaning the power factor of alternator B. Okay, let's try to bring out the solution. If we try to compute for the, what you call this, load current here, IL, designated by IL, it will be the product of a kilowatt times the factor 1000 over square root of 3 times the line-to-line voltage times power factor. Actually, this one emanates from total power for a three-phase balance. This is square root of 3 voltage line-to-line, or just simply BL is a line-to-line times the line current times power factor. Okay? This one here emanates from this. We will try to compute for the value of this one. So it will be the total true power, okay, divided by square root of 3 voltage line to line times power factor. Okay? The one we use under AC circuits or transformers, it is still the same formula. As long as the circuit is three-phase. Right? So for three-phase alternator, this formula actually works. And for transformer, for three-phase alternator, this formula works. They're the same. So for transformer and alternator, this is the formula on how to compute for the total true power. Three-phase. Okay? So this factor square root of 3 here, meaning we are considering a three-phase circuit. Right? So we are given the kilowatts of the load. We convert these kilowatts to watts, we multiply this by 1000 over square root of 3. The line-to-line voltage here, of course, if this is 13.8, this is 13.8, the line voltage here should also be 13.8 kV. So we will convert that 13.8 kV to voltage without decay. So actually we multiply this already by 1000. Okay, so this is multiplied by 13,800. It emanates from 13.8 times 1000. We are converting that kV to B, meaning only voltage, right? Times 0.8, the power factor is 0.8. And if we try to use our calculator, the magnitude of the total line current with this load of 1,600 kilowatts is only 83.673, okay? And if we now try to, express the total line current in terms of the so-called polar form, meaning we specify the magnitude and the angle. The angle should be the arc cosine of the power factor, right? But they should be negative. The significance of this negative here, this is lagging, right? So the magnitude will be 83.673 minus angle 36.87 degrees. It is downward. It's a negative angle theta. So we are given the magnitude, right? So we could compute for the real part and we could compute for the imaginary part. The real part will just be simply the hypotenuse times the cosine of the angle, and that will be 66.938. The imaginary part should be equal to the magnitude times the sine of this. Okay? But we place here a negative thing, meaning it is downward because this negative here refers to lagging. So the imaginary part of IL is 50.2 amperes. The imaginary part. Okay? If we try to specify the total current given by alternator A, it should be capital letter I with the subscript A. It should be the real part of the current minus G, the imaginary part. Okay? And according to the given problem, the alternators have the same load and speed characteristics. So if the total real current is 66.938, when we say they have same load and speed characteristics, they should divide the real current equally. So if we try to compute for the real part of IA, it will be 66.938 divided by 2. Because according to the problem, they will divide it equally. We don't divide the magnitude equally. We will just divide the real current, okay, by 2. So this is 66.938 over 2. And that will be 33.469 amperes. And what is the significance of this one? We want to identify this one, okay? So we could compute for the imaginary part of IA. The imaginary part. Because we are actually given the total magnitude of IA. It is 40 amperes. So if we try to bring out the vector diagram of the current for this is 40 amperes. This is 33.469. Okay? And this side here, we could compute for this one. I will just compute for the angle. The angle is actually cosine of theta. This is 33.469 over 40. Okay, and that is actually 0.8367. And if you try to compute for the corresponding angle for this one, it is actually 33.2 degrees. So this is actually 33.2 degrees. So we are now given the what you call this angle here. So to compute for this, it will just be, it's trigonometry. It's the hypotenuse times the sine of this angle. And the value of that is 21.9 amperes. We are interested in this one because later on, we will be computing for the current delivered by alternator B. And we should, what you call this, express the currents in rectangular form, so we could subtract. So it's a must that we should know the real part and the imaginary part. Okay, for the first requirement for alternator A, the power factor is just the ratio of the real part, real current, over the total value of the current. It is 33.469 over 40. And actually, the power factor of alternator A is 0.8367. This is also lagging. Okay, that's lagging. How about the total true power delivered by alternator A? I will go back to this equation here. Right? We'll go back to this. So it will be square root of 3. Right? The line-to-line voltage for alternator A is 13,800. What's the magnitude of the total current delivered by alternator A? The magnitude is 40 amperes. And what is the power factor of alternator A? It is 0.8367. It's the cosine of 33.2 degrees, 0.8367. We will multiply this by 1 over 1000 to convert this to kilowatts. Okay? And if you try to what do you call this, compute for this one by using your calculator, it is exactly 800 kilowatts. Okay? So you now know why it says they are with the same identical load and speed characteristics, because if this is 1600, we cannot do anything about it. They will share the load equally. So the total true power carried by alternator A is 100 kilowatts. And supposed to be, the total true power carried by alternator B should come out to be 800 kilowatts, but we should bring out the calculation. We cannot just say that this is 800 and this should be 800 without giving the solution. Okay. From the given figure, IL here is the vector sum of IA plus IB, right? It is this. We will add it vectorially. Okay? It seems we are on AC circuit. Because alternating currents, we add it vectorially. It's not algebraically. It got a real part and a so-called imaginary part. So we now know I sub L. We now know I sub A. So we could compute for I sub B. So I sub B will be I sub L minus I sub A. Okay, vectorially speaking. So the value of I sub L, where is I sub L? It is this. This is the total real part. This is the total imaginary part. So this is 66.938 minus G 14.2. That's why after expressing this in polar form, we converted this to rectangular because later on we will be subtracting here. We just anticipated that we are subtracting what we call these rectangular values. So this is IA. It emanates from this. And the value of IA, where is IA? IA is actually, the real part is 33.469 and the imaginary part is 29.9. Where we got this 21.9? Oh, you could use Pythagorean theorem if you like. 40 square minus the square of this and take the square root. Or just take 40 times the sine of theta A. Okay, what will come out will be 21.9. So, IA in terms of rectangular will be 33.469. The imaginary part is 21.90. It's downward. It's lagging, right? Okay, so we subtracting this one, it will still be 33.469. That's why you notice it. The total real part of the current for B is 33.469. And for alternator A, it's 33.469. They divide the so-called load equally, right? So this is minus G 15.2. This is a minus in a minus, so this will now become plus, right? Okay, this will be minus. A minus 50.2 plus 21.9, this is 50.2 bigger than this, so this is minus G 28.3. And if we try to compute for the this is the rectangular form. Okay? So, convert this to polar. Take the ratio of 28.3 divided by this, press arctangent. What will come out will be 40.216 degrees. Should be negative. It is this. The imaginary part is downward also. And the magnitude will be 33.469 divided by the cosine of 40.216 degrees. It is 43.83 amperes. Okay? So the power factor now for alternator B will be the cosine of 40.216 degrees. How come we got this one? Because one of the definitions of power factor, it is the cosine of the angle between the voltage and current. The angle separating the voltage and current, if we try to take the cosine of that, That's one of the definition of power factor. That's why in here, since we now know the angle of the, what they call this, current, and the voltage is always the so-called reference vector, it is at 0 degree. So a 0 minus 40.216 degrees will be 0.216 degrees. The angle separating the voltage and current for B is actually 40.216 degrees. So if we try to take the cosine of that one, that will be the power factor for alternator B. So the power factor for alternator B will be the cosine of 40.216 degrees. It is 0.77636, and this is still lagging. Okay? How about the total true power carried by alternator B? We will be using this same formula here, but we will be substituting the value of I sub B. Okay? So this should be square root 3. The line-to-line voltage is 13,800. It's the same. 13,800 is 13,800. The total current delivered by V is 43.83 as per our computation. Right? The power factor is 0.7636. We convert this to kilowatts, so this is times 1 over 1,000. And if you try to use your calculator, okay, this capital letter P with the subscript B, meaning the total true power delivered by alternator B is still 800 kilowatts. So if you try to notice it, if the load is 1600, if their load and speed characteristics are the same, they share the load equally. Okay, they will carry the load equally. So no one is underloaded, no one is overloaded. They will share the load equally. So this is 1600 divided by 2. Obviously, this will carry 800 kilowatts, and this will carry 800 kilowatts. That's parallel operation of alternators. Okay, guys, this is a good example on the so-called operation of alternators in parallel. Okay, this is Professor DavidJDelosReyes. Good morning from Los Angeles. Merry Christmas, everyone.